All right, let's get started. So last week of classes, as I'm sure you're aware, and Wednesday is the last week of this class. The assignment, the asteroids assignment, is due Thursday or Friday if you take a late day. And the final is Wednesday, December 12th, so a week from Wednesday. All right, let's get started. The correct time, I had it wrong for a while in one place, is from 3:30 to 5:30. So for the regular section, for this section, the exam period is 3:30 to 5:30 in here or upstairs, depending on your last name. And it's the same as it was for the midterm. And for the hybrid section, it's in here from 6 to 8, the same day. Be sure to bring your U card, and you can bring two sheets of notes this time. Okay, any questions or problems about anything? Is asteroids going okay? Yeah?
So how can you make it like stay going one direction? Why should we just keep going like this?
How to keep, like an alien ship moving?
Sorry, alien ship, sorry.
Keep the alien ship moving in one direction?
Yeah.
Well, you set a direction and you don't change it, I guess.
Well, because like I made it choose randomly between left and right every time it spawned, but then it seems like it keeps choosing.
So it starts going and it's moving back and forth like that?
Yeah.
Well, it has to be that you're changing, you've got something, it's supposed to change direction every second, okay? But it's supposed to, like if it starts over here, it's supposed to move for a second and then either go a radian up or radian down or keep going in the same direction. You should never back up. So maybe your calculation where you're having it turn, you've got the wrong sign on it. That's all I can think. Yes?
Is it possible to place the alien ship off the screen and then have the countdown timer maybe start moving after 5 to 10 seconds? Or do you have to place it so we're the same time?
Okay, so he's asking, is it possible to place the alien ship off the screen, only start moving it so that only start moving it when you actually want to appear? I mean, you can place it, it turns out there's a part of the screen that you can't see when it wraps around, but if an asteroid runs into it while it's there, it's going to explode.
Will the asteroid run into it because they'll wrap around to the other side of the screen?
Yeah.
Okay.
Yeah. No, the way to place it, you can create the alien ship, and you can start the countdown timer on it. Just don't add it to the game until the countdown timer expires. There's like an add participant method that you call. So don't call that until you want it to enter the game. Any other questions? Yeah?
How did you get the ship firing sound to work? Because like when I do it and I just put the sound every time it shoots, it sounds different from when I start firing.
Okay, so I've had this question a couple of times. How it has to do with firing. So if every time a bullet is fired, you play that sound, what's going to happen is it'll be partway through playing the sound, assuming you're firing quickly, and it'll start over. So it's going to sound staticky or clipped. The thing to do is, when the fire button goes down, start it on a loop. I'm thinking of the thrust for the ship. So thrust for the ship, as soon as the thrust button goes down, you start playing a loop, and you just let it loop and stop it when the button comes up. For firing, that's more discrete activity. But I guess the same thing can apply to as long as the fire button is down, put the fire sound on a loop. Any other questions? Okay, so in lab tomorrow, the TAs are going to go over the sample exam that's been posted for a while. And so that's a good way to prepare for the final. On Wednesday, what I'm going to do is I'm going to answer any questions you have, and then I'm going to go over a different final. I have slides posted which are sort of a final review, but in my experience it doesn't go very well just to go through the slides. So I've got the slides up now. What you should do is look at them between now and Wednesday, and maybe it'll jog your memory about questions you have. And I'll answer questions as long as there are any, and then we'll go over the final, and that will probably cause more questions to be asked. So that's what I have planned for Wednesday. Okay? All right, so today we're going to talk a little bit more about algorithms and data structures, which is something you'll be confronting in 2420 if you take that. And I'm going to start with a very simple algorithm. You're given a sorted array, and you want to find out if a particular number is in it. And the first one we're going to look at is linear search. Linear search just says, you write a loop, you start at the beginning, and you look until you find the 45. Or, when can you stop? If you know the list is sorted and you're looking for 45, yeah. Right, if you find 45, that's good. You report you found it. If you find a number larger than 45, you know there's no chance you're going to find it anywhere else. So you can stop then. So you don't necessarily have to go all the way to the end of the array. So let's just not much to say about it, but we look in the array, we compare 45 to 1, we're imagine a loop doing this, and that's not it. And we look at 3, at 7, at 9, 11, 15, 23, 24, 30, 33, 39, and finally we hit the 50, and we know that there's no point in continuing. And we can report it's not in the array because it's sorted. And I don't know if I counted right, 1, 2, 3, 4, 5, 6, 7, 8, 9, yep, 12 probes. So we had to look 12 places in the array. Okay, how can we do better? When I was a kid, I remember going to church, and we had a hymnal, and there were about 500 hymns in the hymnal. And they would say, okay, we will now sing hymn number 172. And I made a challenge to myself to turn to hymn 172 by only looking at 5 pages. That was my goal. So I try to turn right to it, and then if that wasn't it, I'd adjust my search. And I could generally find it with 5 probes. Okay? So how can we take an idea like that and apply it here? Yeah?
Instead of like guessing at the top, you just guess at the middle.
Okay. Okay. So in the hymnal, I have the advantage that the hymns were consecutively numbered. They don't have that in this array, so you can't really guess where it might lie. So the suggestion is just to look in the middle. So let's see if 45 is in this list. So I'm going to look right in the middle. That's the 24. Now, first of all, how do you calculate the middle? How do you know where the middle is in an array like that? Yeah? Yes, the length of the array divided by 2, or another way to think about it is the average of the left index, which is 0, and the right index, which is whatever it is. Okay? All right, so we see a 24. That's not 45, so we need to keep looking. But how can we speed things up? What does the fact that that's a 24 tell us about where 45 has to be? Yeah?
You toss out the left portion.
Right, we don't have to worry about anything to the left of the 24, because we know everything to the left of the 24 is smaller than 24. So we can throw all that array away. So the thing to see is that by doing one probe, by looking at one number in the array, we have ruled out actually half of the elements, actually one more than half the elements. Because we know 24 isn't it either. So we've cut our problem size down from searching an array this big to searching an array that big. Okay? So where should we probe next? Yeah?
In the middle of the array, sorry.
In the middle of what's left. And so to do that, we would figure out the index. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So that's index 8. 9, 10, 11, 12, 13, 14. So we would take the average of the 8 and the 14, and that would be 11. which would be 8, 9, 10, 11. It would be right there in the middle. So if you're doing a binary search, you've got to know not just that you're searching an array, you need to know what's the left index and what's the right index of the portion that you currently care about. So we'll probe right there, and we see there's a 50. So that's not it. It's not a 45, but what does it allow us to do? We can ignore everything from 50 on to the right. Again, we're throwing away half of what's left. Okay? Now we've got, our array just has, the subarray we care about contains 3 elements, so we'll probe to the middle of it. And that's not right, so what can we throw away? Looking for 45, so we know that 33 and everything to its left is too small. Even though we don't have to look at it to know that because the array is sorted. And that leaves one place to look. And that's not 45, so we can report it's 45. But let me tell you another cool thing. When you don't find the element, you also know where it would be if it were in the array, or where you should put it if you were to put it to the array. Where should we put the 45? Once we find out it's not in there, if we wanted to do an insertion. Yeah? Right, one spot. So when you home in on a single element, that's not the right one. If the element you're looking for is bigger than the one you're looking at, bigger than the yellow element, we can just stick, so we stick the 45 in between the 39 and the 50. If the thing we're looking for is smaller than the 39, we put it just to the left. So this not only tells you whether something is in the array, it tells you where it ought to go, which is kind of nice. Okay, so that just took 4 probes. And the other way, I think it was 12. So is this a big deal, the difference between 12 probes and 4 probes? Okay, people seem to be saying yes. So does that mean binary search is 3 times faster than linear search? One takes 12 probes, one takes 4 probes. How much faster is it? Yeah?
It'll be somewhere between 12 and 4 times faster. Sorry, 3 times faster.
Okay, so for this array,
Yeah, for
you're
that.
saying it's between 12 and 3 times faster. That was you said, right?
Yeah.
We may get lucky and find it in the first place we look. But let's assume the lookups are always unsuccessful. That's the worst case. If lookups are unsuccessful, then you're going to have to look the maximum number of times. So in this case, it's going to be 3 times faster. But in general, as the array gets longer, it becomes a bigger and a bigger deal. Okay, so I'm saying that if you have an n-element sorted array, and you do an unsuccessful search, on average it'll take n over 2 probes for linear search. So where does that average come from? How can we say that on average you got to look at half the elements? Yeah?
Because on average, there's the same amount of volume for all of them. If you just go through
Okay. So we said on average the thing you're looking for will tend to be in the middle of the elements in the array. Another way to think about it is sometimes you'll be looking up a very small element and right away you'll find out it's not there. Sometimes you're looking up a big one, you'll have to look through the whole array to find out it's not there. But on average, you're going to have to look at about half the elements. Okay? So if the array is 1,000,000 elements long, on average, an unsuccessful search is going to require looking at 500,000 elements. Okay, and then I say here that an unsuccessful search with binary search, the second algorithm we looked at, takes log base 2 of n probes. Now where does that come from? Log base 2 of n. Go for it.
how many times you divide it in half.
Okay. He said it's a number of times you can divide the array in half. Essentially every time you do a probe, you're throwing away half of what's left in the array. So you cut the array in half, you cut it in half again, you cut it in half again, you cut it in half again until you're down to 1 element. And the number of times you can divide something by 2 before you get down to 1 is the log base 2 of n. So, if it takes 500,000 probes on average for on a million element array, how many probes will it take for a binary, unsuccessful binary search on a million element array? In other words, what is the log base 2 of a million? Does anyone have that committed to memory? I'll tell you, yeah.
About 20.
About 20. Here's the rule of thumb. What is 2 to the 10th power? Yeah?
1024.
1,024, also known as about 1,000. So the 10th power of 2 is about 1,000. And how many times can you divide the 10th power of 2 by 2 before you get 1? 10 times, right? So the thing to remember is that the log base 2 of 1,000 is about 10, and the log base 2 of a million is about 20, and the log base 2 of a billion is about 30. So that tells us that on our million element array, linear search does 500,000 probes. Binary search does 20. Okay, that's a massive difference. Right? Make it a billion element array, then you've got 500 million versus 30. So log base 2, log, doesn't matter the base, log grows very slowly compared to even a linear curve, let alone a quadratic or something. So this is an amazingly good algorithm compared to linear search. So why would we ever do a linear search? Yeah? Okay, so if your array is not sorted, if the array is already sorted, you might as well do a binary search. If the array is sorted, to do a binary search. If it's not, you got to ask, is it more efficient to search the array with a linear search or to sort it first and use a binary search? So what do you think? If you had a million element array that wasn't sorted and you got to choose between just going through the whole thing to see if you can find the number, or sorting it first and then do a binary search. Which do you think would be better? These are the kinds of decisions you have to make when you're writing programs. And you could say, well, I'll just write it both ways and time it, or you could learn how to, do a back of the envelope computation and figure out what's better. So what do you think? Should we sort our million element array first with quick sort and then do a binary search, or should we just do just write a loop to go through? Anybody want to take a position? Yeah?
Sort it first, because then you'll be able to use the sorted array again.
Okay. So he said sort it first because then you can do multiple searches. You don't have to sort it again, except you just have to sort it the first time, and then you can do multiple searches. And that's true. If you're going to do enough searches, you might as well sort it. But what if you're only going to search it once? Is it worth sorting? Yeah.
It's worth sorting still.
Okay, and what's your reasoning? He said it's worth sorting.
The speed for sorting it with quick sort is going to be the log of something, the log base of 2 of something, or log of something, plus this log, and that's still going to be much faster.
Okay, so his reasoning was that we could sort using quick sort in logarithmic time, and then do our binary search in logarithmic time. And if both those were true, you would be right. But how long does quick sort take? Yeah. It's n log n. Okay, so quick sort takes linear time, takes worse than linear time, n log n time. It's exactly the right reasoning, but you just had a little fact wrong. Okay, so sorting is going to be more expensive. It's a more complex algorithm than a linear search. So if you're just doing one search, you'd be better off just doing a scan. Okay, so those are the kinds of trade-offs you weigh in your mind a lot when you're trying to figure out the best way to write a program. There's what I said before. Okay, now, before we look at linked lists, we've got a program here. That compares, that times out sorting, not sorting out. I'll close this down. Okay, so what this does, what I'm timing here, is I figure out the average amount of time it takes to read in a file of words and then search for a word in that file. And I compare that to the time it takes to read in a file once, save it in an array, and then do a linear search for it. So the one way, in fact, let's compare the methods. So this is time direct lookups. What it does is it opens a scanner into a dictionary file and then does a linear search through the scanner. Just like that. So it doesn't use an array. It just goes through the scanner the way you're used to and tries to find the file. It tries to find the word and reports whether or not it's there. So that's what one of the methods does, and it computes. It does it 10 times. I don't need to do that first. So it does it 10 times down here and displays the amount of time. Oh, I know why I'm doing that. And then we compare it. And then we do the same thing, except we read the file in and then do a bunch of searches and get the average amount of time. So which do you think should be faster? On average. Reading from a file, let's say you did it 100 times. Read from a file, and then read from a file again, and read from a file again 100 times looking for a word. Or to read the whole thing into an array, and then do 100 searches on the array. Does it make any difference? Yeah. Okay, you said the array would be faster because you can categorize the items. So what do you mean by categorize? Oh, okay, so she's suggesting that we could take advantage of knowing what the words are and organize them so they're searchable more efficiently. But we're not going to do anything fancy like that. We're just going to read all the words in. In fact, if we go look at time cached lookups linear, you see we're just going to go through the scanner and we're going to append them to an array list. We take the words out of the dictionary, append them to the array list, and then we're going to time how long it takes to do a linear search on them. Okay? You're right that it's faster to read the words in and then operate on the array, but why is that? Yeah? Okay, you said reading RAM is a lot faster than reading from disk. Okay? Anytime you have to go to secondary memory, it's just slower. Now, it was really dramatic when I had a laptop that had spinning media in it, because that's really slow compared to a processor. But now that I have solid state drive in here, it's more competitive. But still, anytime you have to go out and read from a file, it takes an eternity compared to how long it takes the processor to run. So we can compare the two times. So I'm going to do 10 lookups that involve reading the file each time. So I'm going to do 10 reads, going through looking for the file, and then compute the average. Do the same thing for reading in the file once, and then searching the resulting array 1,000 times. Both times I'm computing an average. Why am I doing one 10 times and the other 1,000 times? Why not do them both 1,000 times? Yeah.
If you did the first one 1,000 times, it would take a really long time.
Yeah, it takes, I don't want to do that slow operation 1,000 times. It just takes too long standing up here. Okay? But we're computing the average, so it shouldn't matter. And again, my timing is kind of sloppy. The only thing I'm doing is I'm making this call once and ignoring the time it takes, just so I can get everything loaded in and get the virtual machine up to speed. But I'm not doing a very careful job with it. But let's compare. Okay, so on average, it's, you know, the difference is like a factor of 6 or something. So it's not as dramatic as I would have hoped. And I think it really ought to be a more dramatic difference. I'm not sure why it's like that. I think the first time reading the file is slower than subsequent times reading the file. Because what happens is the first time reading the file, the pages from the file end up getting read into RAM. You can see that there's an overhead reading the file. But let's look down here. Here what I did was I read the words in. I didn't conclude the time it took to read the words. I just got them into array and then did a timing experiment, once doing a linear search and once doing a binary search. So there you can see that the binary search is many orders of magnitude faster than the linear search on this particular file. So I'm just trying to show you again the advantages of a good algorithm over a bad one. Okay, you've known for a while now that there are two kinds of lists that Java provides. There are array lists, which we learned how they worked a couple months ago. Inside an array list is an array that contains the elements of the list, and when the array fills up, a new one is allocated that's roughly twice as big as the original, and the old elements are copied over, so that there's room to grow. We don't have to do a copy every time we insert an element. And we saw that on average this performs pretty well. There's another one in the collections, one of the collections classes called linked list. And that's what I'm going to talk about now. So what I've got up there is a picture of a linked list, sort of the internal representation of a linked list. In every one of those boxes, there are 4 boxes up there. Each one of them is an object, a separate object. The errors are references. So the variable list contains a reference to the first object. It's a link object. The link object contains 2 things. It contains, the first link object contains 1, and then a reference to the next link object. And that link object contains 7, and a reference to the next one, and so on. And that final link object contains an 8, and then what's that stored at the end? It's not an arrow. That's slash. What would you store if you're, well, we'll talk about that in a minute. So here is the actual class, the link class. And you can see there are 2 instance variables, value and next. So for each link, value is the number that the link contains, and next is a reference to the next link in the chain. We have a constructor to make a link, and then we have methods to get and set the value, well, to get the value, to set the value, to get the next link, and to set the next link. So if you cut open a linked list, you see something like that. That's the internal representation. That's not what the user sees, but that's how it's organized inside. So let's look at that. What list would that represent? How many elements are in the list that that thing up there represents? What do you think? Okay, you said 4, sure. And the 4 elements are 1, 7, 4, and 8. Okay, let's play around and see look at some code that it takes to manipulate linked lists like this. So first of all, what would it take to build a linked list? Suppose you want to build that list, and you've got these methods. You've got this constructor here to work with. So you got a constructor, you give it a value and a reference to a link, and it will return to you a link that contains the value and references that link. So how would you build the list 1748? Yeah?
Recursively?
You can do it recursively. You can also do it iteratively. So we, typically for linked lists, we prefer doing things iteratively. So this is an example of a linked data structure. And you'll see, in 2420, you'll see other linked data structures like binary trees. And for binary trees, you typically do recursions. Okay, how do I build it?
You could just build it all in one line. Because like, constructor took a next, so you could just have a new link.
Okay.
And just keep building.
So it's true, we could build it all in one line, but that would be, it'd be kind of confusing. So let's simplify things. Ignore everything except that last link up there. That box that contains an 8 and a slash. Okay, what that we're going to represent that slash, which means no more, with null. So how would you build just the link that contains 8 as its value and null as its next? Using that constructor right there. Okay?
Just plug in 8 and null.
Yeah. So we could say list equals new link 8 null, and we would have that picture up there. Okay, but we want to get to this picture. So how could we add 4 to the beginning of that list? How could we make it, now that we have a reference to that last link, how can we make the list look like those last 2 boxes? So a 4 box pointing to an 8 box. Yeah.
Maybe like the first parameter would be 4, the last one, or the second parameter would be list.
Right.
As you said.
So this is what he said. We create a new link that contains 4 as its value and refers to list. And remember, list referred to that 8 box. And then, once we have that link, that becomes a new value of list. So before, list referred to, before we started this, if I back up, list referred to this box right here. So we're going to create a new link that's going to contain an 8 and refer, we create a new link that contains 4 and refers to what list used to refer to, which is this. And then this thing here becomes a new value of list. So we're just working backwards. We're adding things to the beginning. So to add on the next thing, we do that. We say list equals new link 7 list. So this box contains 7, and this refers to the thing that list referred to at the time the link was created. And now list refers to this, and then finally you go there. And that's how you can build a list. Yeah?
Do you have to go each value one at a time, or can you not just do like one list?
Well, that's what he was suggesting before. We could have said new link 1, comma, new link 7, comma, new link 4, comma, new link 8 null, close paren, close paren, close paren, close paren. We could have built it in one mouthful. But I chose to build it more iteratively this way. Okay? Now, what I'm claiming is this is an alternative way to represent a list as opposed to a dynamic, instead of using an array. So array list has an array internally that doubles in length periodically, and a linked list object in Java contains within it a linked list like this. So why would this be preferable? This seems a lot more complicated than an array. Yeah?
It's faster for adding.
It's faster for adding things. So what's it take to add, suppose we wanted to add something right here between 1 and 7. We want to add some number that's in between the 1 and the 7. Okay? And imagine the list is actually 1,000,000 elements long. Now, if that same list were in an array, what would it take to add an element between the first and the second element? Have 1,000,000 numbers in an array, yeah.
You have to find the index if you want to push it, but then you have to push all the other ones over
Right.
the spot.
So if you want to insert into an array, we'd have to make room for it. We'd have to copy all the existing elements over by 1 to open up a space to put the number in. So we'd be copying almost 1 million elements to the right so that we could plug something in. And that's very inefficient. Now, adding to the end of an array list is efficient. There's nothing to copy over. But adding it to the middle involves shoving everything over and then placing a number in place. Okay? What about adding to a linked list? How would you add something between the 1 and the 7? Does that involve copying 1 million things? Imagine this chain were 1 million long. Yeah?
All you have to do is make the one refer to the and you refer to
Okay. So what he's saying is, just imagine we stick a box here that contains the new number. We just got to make this guy point to the new box and have the new box point to the 7. Just splice it in. It doesn't have to be contiguous. The problem with array is all the numbers have to be contiguous. And so if you want to stick something in the middle, you got to open up some space. And that involves copying. But here, these references can be all through memory. They don't have to be next to each other. So let's look at that. So I want to insert, in this case, I want to insert a 5 between the 7 and the 4. So let me show you that this is the step of doing an insertion. First, I have to get a reference to the 7 box, because I want to insert after the 7 box. So I say before is list.getNext. So now before refers to this box right here. Okay? Then I'm going to create a new link that contains 5, which is the number we want to insert, and refers to before.next. So this new box here contains our new number, and it refers to the same thing that before refers to. Okay? So now we have a reference to before, the 7 box, and we have a reference to the new link. So how do we finish the picture? How do we finish splicing this 5 in between the 7 and the 4? What has to change about the picture? Okay? Someone just motion, yes?
change before's reference.
Right, we got to change what's stored here in this reference to push to point at new link. So what would the code be? This box is referred to by before. So what do we do to before? Say again? Okay, we have to change the link. And the method is set next is the method. So we're going to do before.setNext, and what do we pass as the parameter to set next? What are we going to change before's next value to? To new link. So there's what it looks like. Something. Oh, well, some reason I have after there. I should say before. Let me fix that while I'm thinking about it.
On the second line too, you have after.next.
Obviously, I changed my mind at some point. Okay. So it just takes those 3 operations. We first get a reference to the thing after which the new element's going to go. We create the new element, and then we complete the splice by having the predecessor now point directly to the new thing. And then we don't need before a new link anymore, and we're just left with that. Okay, so now we've added to the list. And does it take any longer to add into the middle of the list? Does it depend on the length of the list? Does it take longer to add to a new second element to a list of length 10 or compared to a list of length 1,000,000? Does it matter? No, all that matters is this, you're just doing something right in this area right here. It doesn't matter how much stuff is to the right. Okay, so that's good. Now, what would code look like if I wanted to say, given a list like this, to print out everything in the list? what would a loop look like that consumed a list? Walk down the list. Yeah?
I was just calling get next.
Okay. So you call get next over and over again until what? Yeah?
Until you hit null.
Until I hit null. So it's a while loop. So it looks like this. I'm going to let link be list. So link will be pointing to the first link object. And while link is not null, what I do is I print out link.getValue, and then I set link to link.getNext. So what will happen is, initially, link will be pointing to this thing here. After one time through the loop, what will be link referring to? It'll be referring to this one. And the next time through, it'll be referring to that one. And then that one, and then that one, and then what will happen? What will the value of link be? We're going to say link equals link.getNext. If link is referring to this box, the new value of link will be null, which will end the loop. Okay? Now what if I was really nasty, and before I did this, I went and I changed next. I said, I changed this to refer to, back to the 7 here. So imagine I changed this so it referred all the way back and referred to the 7 box. So I've created a circular structure. It's not really a list anymore. What would that loop do then?
It would just enter infinite loop.
Yeah, it's an infinite loop. It would never hit null. It would print out 1, 7, 5, 8, 7, I'm sorry, 1, 7, 5, 4, 8, 7, 5, 4, 8, 7, 5, 4, 8. It would just be stuck in that loop. So that code here would only work for true lists, not for this kind of circular structure. Okay? This all sounds good. Why do we bother with arrays now? Yeah?
Because arrays have an index.
Okay? You said because arrays have an index. So, let's say you have a list of length 1,000,000 represented as an array. And you want to get the 500,000th element, the middle element of the list. What do you do? How long does it take to get that element? It's really fast. You can go straight there. Because the array is contiguous, and so it's easy for Java to figure out where the 500,000th element is. Now, suppose you have a structure like this, a linked list of length 1,000,000. What does it take to find the 500,000th element? How are you going to do that? Yeah? Right, you're basically going to have to do a loop like this, counting as you go until you've gone 500,000 steps. So you just go 500,000 times, and finally you'll arrive at your destination and you'll get the element out. So that's a disaster. So there's a trade-off here, and that's often the case with data structures. You can't say that a linked list is better or worse than an array list. It just depends on how you're going to use it. If you're going to do a lot of random access stuff, you want to use an array list. On the other hand, if you're doing a lot of insertions into the middle of things, you tend to use a linked list. It just depends. Some things are fast, some things are slow. Yeah?
Is it possible to convert this to an array list? Say we want to insert 1,000,000 different things and then change it to an array list.
I mean, yeah, you could, this loop right here that's going through the array, instead of printing out the elements, it could be appending things to an array and converting it to an array list. But that's an expensive operation. So here's the thing to realize. Going to a specific element is a lot cheaper in an array list than in a linked list. But what about visiting every element in order? In other words, this loop visits every element in the linked list. And you can imagine the corresponding loop for an array list. Visit that, you'd have an index and you'd increment it and visit every element. Those two loops are about the same complexity. So if all you're doing with your list is trying to visit every element in it, you might as well use either one's okay. Linked lists just start to suffer when you need to do true random access, one element somewhere. Okay. Any questions or observations about this before I move on? Yes?
Would this be faster to sort as well?
He's asking, would it be faster to sort? Good question. Well, let's think about, say, for example, selection sort. One operation is comparing elements. One operation is swapping elements. I guess you could, if you took selection sort as written, which uses indexes, it would be hard to implement. It would be very inefficient on a linked list, because you're letting the index run through it. Every time you got to look up an index into the list, it's slow. You could modify it though, so that you, instead of using indexes, you went through it more like this. As long as you remembered not the largest element, or not the smallest element you've seen so far, but you kept a reference to the smallest element you've seen so far. You could make sorting work. So you could make selection sort work on this. But usually sorting is done on arrays, not on linked lists. Any other questions? Okay, let me ask you one. Where's the worst place from the standpoint of performance to add an element to a linked list? Yeah?
First element.
Well, now that's back. The first element's the best place for a linked list. Because all you got to do, if we want to insert something before the beginning of this list, we just create a new element that refers to the old one, and we're done. So it's not the first element. I heard it over here. The last one is the bad one. And what's bad about adding to the end?
You have to find the end.
It's finding the end is the problem. If you're already at the end, it's easy to do. It's finding the end. So for that reason, Java's linked list class isn't structured like this. It's what's called a doubly linked list. So it has every link has a reference not just to the thing that follows it, but to the one that comes before it. And we maintain not just a reference to the beginning of the list, but also to the end. So that as long as you're working near the ends, it's efficient. It's the middle then that becomes the problem. And that's an important optimization, because adding to the end is a very common thing to want to do. Okay, let's take a break for a few minutes, and we're going to actually look at this in Java in Eclipse, see what it looks like. All right, let's get going again. Yeah?
I just had a question about like how the iterators work. Just I remember reading about it in the book a bit, so it didn't really quite make sense.
Mm-hmm.
And I know they kind of go like hand in hand with list on certain elements.
Okay, so he's asking about iterators. So an iterator is an object that I don't support it in my implementation, but you can obtain an iterator from a linked list, and that gives you a way to iterate through the elements of the list. And you can obtain two different iterators for the same list, and you can have two different loops, assuming the iterator is separate.
So it's kind of like a scanner almost.
It's sort of like a scanner. But basically, if you use a for each loop to consume a linked list, you're using an iterator. And actually, I have something I'll say about iterators at the very end here. I want us to complete the implementation of this linked list class, my linked list. And you can see the representation. What I've chosen is I'm going to keep track of the size of the number of elements in the list. And I'm going to keep track of the linked structure. I got the root of the linked structure that contains the elements. Now, this is redundant. I don't have to store the size, but why am I storing the size here? Yeah?
So that it's easy to get the size if they want to know the size of the list.
Okay, he's saying so it's easy to get the size. Okay, there's a get size method, and if I'm not storing the size of the list, what's it going to take to determine the size of the list? You have to walk the entire linked structure and count how many elements there are. And that turns get size into an expensive operation. So that's a slight optimization. Okay, so at any given time, we're going to contain a linked structure like we were just looking at pictures of. And size will contain the number of links in it. So to create an empty list, clearly its size is 0. What linked structure? That's not right. How do we initialize the linked structure? What's an empty linked list look like? Yeah?
Root equals null.
Right, we'll just set this to null. So initially our list is, the root of the list is just null. There is no list, no elements, and the size is 0. Okay. Here's my get method. So the get method, I give it an index, and I want to get the number that's stored at that index of the list. And I've got a method called getLink that will give me back the link. Say index is 5. It'll give me back the 5th index in the list. And then I can extract the value and return it. So getLink is what's doing all the work. So getLink has to walk down the list till it finds the box we care about and returns the box. We extract the value and return it. Okay, set is the same thing. If I want to change what's stored at an index in my linked list, I get the appropriate link and change its value. Again, getLink is doing the work. Okay, add first. I want to add an element to the beginning of my list. So I've got root is some list. How do I add a new link to the beginning? And we could, suppose I want to add a new link to the beginning of this, before the 1. What do I do? Yeah?
You just pass in what you want to be in the element and then create a link to the list you already have.
Okay, so it's going to be like, when I talked about building a linked list, it's going to look something like this. I'm going to create a new link that contains the new number with a reference to the old list. Okay? So I'm going to change root to be a new link. What value will be stored in that link? Val. And what will it refer to? The old value of root. So that's all it takes to add to the beginning of the list. Just create a new link that contains the value and refers to the old list. Well, that's not quite all. What mistake did I just make? A link structure is fine. Yeah?
Increment size.
Right. I need to increment size to remember that there's a new element there. Okay. Now, let's add an element to the end of the list. Yeah.
If root is null, wouldn't it be the same thing we just did?
Okay, so if root is null, it's going to be, there's nothing in the list, so we'll create a new link. The link will contain the value and then null, so it's just a one-element linked list, and our size is 1. Otherwise, what do we have to do? Okay, let me get in the back there.
I was just thinking for if root equals null, couldn't you just do add first?
Couldn't you just do what?
Add, like the add first method.
Yeah, you're right. I could replace all this here with just a call to add first. Why not? It's a good suggestion. It's going to do the same thing. Okay? Now, if it's not null, conceptually, what do we have to do? Let's go back to a picture here. What would it take to add to the end of this list right here? What has to change in the picture to add an element to this list? Yeah.
Root equals new link, comma root.
Okay, so in this case, list is playing the role of root. But we don't want to change root. Root still needs to refer to that box. It still needs to refer to 7, to 4, but still needs to refer to 8. What are we physically changing in this to add something to the end, as opposed to the beginning? Yeah?
I don't know, maybe we want to get rid of the null at the end of the first.
Right. We've got to create a new link and put a reference to, replace this null with a reference to the new link. So first step is to get a hold of the last link in the list and then modify it. Okay? How can we get a hold of the last element in the list? Yeah?
Get link with size -1.
Okay. Get link, we can use get link. We got to give it the index to get. So let's do this. Link. The index of the last thing will be size -1. Now we got the last link in the chain. How do we add something? How do we add something for it to refer to, a new thing? What do we do to last? Okay.
Set next to a new link.
Right. We set next to refer to a new link that contains the value
Value and then null.
and null. So let's do a little bit of list surgery. Get the last link, and then we create a new link for it to refer to. We call the set link method, the set next method to make that work. So that splices in a new element. And then we have to remember we've added a new element here.
Yeah.
Okay, that's how you add last. So that's really the first fairly complicated one we looked at. So let me let you look at it just for another few seconds here, see if you have any questions about it. So we're adding to the first, we're able to add to the last. I don't think I have us implementing add to the middle, but maybe I'm wrong. Okay, returning the length of the list is easy. Okay, the only one I have left here is get a link. So if the index is out of bounds, we'd throw an exception. Otherwise, what do we do? We've got to traverse the list like with that while loop I wrote before. So where's our starting point? Let's go look at a picture here. Suppose you've got this list and you want to return the link that's at index 2. What are you going to do? Where do you start? Where do you end up? Yeah? Okay, you're going to start with what list refers to here. And you're going to do a get next, and you're there. So we made 2 hops, and that gets us to where we want to go. So let's let node start out as being the same thing as root. We don't want to modify root, so I'm going to copy root into node, and then I'm going to say while index is greater than 0. Because if index is 0, we're just going to return node. We're there already. So what do we do while index is greater than 0? How do we change node to be the next thing in the link, the next thing in the chain? And our index decreases. So we just keep going node.getNext until our index gets down to 0. And when we're done, we'll be at the right spot. And we can return node. Yeah?
Can you change the index like that even though it's passed in as a parameter?
Yeah, you can always change the value of the parameter.
Okay.
And it doesn't have any effect on
It's just
the
something.
point of call. Okay, so there's our get link method. Now, I've got a MyList test here I'm going to run to make sure that I didn't make any mistakes. Okay, now let's do a timing experiment. That's sort of the theme. I have MyList timer. Let's see what it does. It does a timing experiment, so it sets size to 50,000. It does an experiment on an array list, and then it does an experiment on a linked list. Then it doubles size, and it does an experiment on array list and experiment on linked list. Okay? Now let's look at do timing. What's it doing? It's figuring out how long it takes. It's doing a bunch of add firsts and deciding how long an average add first takes. And then it does a bunch of get calls. So it tries to do a get operation for every index in the list and sees how long that takes. So what would you expect to see as a result of this? Let's start with the, let's see, we're timing how long an add first takes and how long an average get takes. So array list versus linked list. Who's going to win the add first competition? Yeah? Yeah, the linked list should. We've already made that argument. It's going to start, both cases, it's going to start with an empty list, and it's going to add, it's going to, 50,000 times, it's going to add something to the beginning. So each time you add the beginning of the linked list, it's going to be fast. Each time you add the beginning of the array list, each subsequent add is going to take longer and longer because of the copying involved. What about the get operation, where you start with an array that's already of length 50,000 or 100,000, and you do random access to every element in it? Which one should win? Yeah?
The array list?
Yeah, the array list should win, again, because we've already made that argument. So let's run it and see what it looks like. Okay, so the first set of numbers was for 50,000, and the next set's for 100,000. Let's give him the time in microseconds. Okay, so for 50,000, so you see here that the add first on the array list takes 9 microseconds, but here On the linked list, it's 0.01 microseconds, so way faster. On the other hand, the average get operation is like 5 nanoseconds for the array list, but it's 45 microseconds on the linked list. So the difference is dramatic there as well. Now compare what happens when you double the length of a array list. Well, you can see that I'm sort of trying to compare these two numbers here. I don't think I have any big point to make there. Let's just notice that it's more instructive to compare array list to linked list. Okay, so just as we expected, the add firsts favor the linked list, the random access favors the array list. All right, this is the last thing I'm going to show you here. This is not using the code we just wrote. This is using Java's linked list class. So to create an empty linked list of doubles, I go and add 1,000 numbers to the list in a loop. And then I go through the list, and if I find, I want to delete 500 from the list. So I'm going to search through the list, and when I find 500, I'm going to remove it. Because there's a remove operation. It says remove an element from the list. What will happen when I run this code, when I run for each example? Do you see any problem with that code? Yeah?
Is it going to like essentially iterate the first element, then it's going to iterate the first and second, grab the second value, and first, second, third, and third?
No, it's not. It's not an efficiency problem. This for loop is behind the scenes. It's using an iterator object to move through the list. It's just like you'd expect. Okay? Let me run it. Okay, what we get, the reason I'm showing you this example is because eventually, if you haven't already, you'll see something called a concurrent modification exception. So we got a concurrent modification exception on line 970. Well, that's the wrong place. I'm going to look at my code, line 23. So what can be going on? What do you suppose a concurrent modification exception is? What's that sound like? Yeah?
It's probably because you're searching for lowercase d doubles and a list of big d doubles.
Okay, he said it's because we're looking for a lowercase d double and a list of uppercase doubles, but that's not the problem. Java converts back and forth between them, so that's not the issue. Yeah?
You're modifying the list as you go through it?
You're modifying the list as you go through it. When you're using an iterator, which a for loop does, a for each loop does, you're not allowed to modify the thing that you're iterating over. So what happened was, we removed the element, but then when we tried to get the next element, it complained. It says, I notice you've modified this list, I can't iterate over it anymore. And you can imagine what would happen if you're iterating through and you removed an element from the inside of a linked list. Now all the, some other code modified the list while you're iterating over it. So now things point to the wrong places and you get bad results. Yeah?
If you had a break right after like a list got removed, would it work? Or?
Yeah, if we had a break right here, we'd never get the exception because we would never have, as long as you end the iteration, you can modify it.
Right.
Yeah?
Why does the break solve that issue again?
The break does solve the issue. But suppose I wanted to delete 500 and 750. I didn't want to end the loop. Right? If you're willing to end the loop, that's fine. So the thing is, what an iterator object is, the iterator object is a separate object from the list. And it just keeps track of where it is in the iteration. It has a reference to the list, and it keeps track of where it is in the iteration. And if that list modifies itself during the iteration, then all bets are off. That's why it throws an exception. It assumes the thing it's iterating over is not going to change. Now, I want you to compare it, what we just did, to another way. You can also use an iterator directly instead of with a for each loop. And then it looks like a scanner. So what I do is I ask the list to give me back a list iterator. And then I have a has-next method and a next. So it works just like a scanner. So I'm saying while there is a next element, get the next element. If it's 500, remove it. Okay? So you can, when you use a for each loop, it's just automatically calling has next and next for you behind the scenes. So let's run this one and see what happens. That's not supposed to happen. Let's make sure I change this over. I just want to call the one, iterator example. And it runs and nothing's printed out, nothing bad happens. What's the difference here? Both cases we're using an iterator. In one case, the iterator is behind the scenes in the for each loop. Here, it's explicit. Yeah?
You're not using a for each loop in this case? So
well, we're not using a for each loop, but that's not the important difference. Let me show you up here. Okay? Wish I can't quite get them all in there. Okay? Notice the difference right there. List.remove versus iter.remove. So when you're iterating over something, when you're using an iterator, as this for each loop is, you're not allowed to go and modify the list. But you can ask the iterator to modify it for you. So we're not making a method call to the list and asking it to remove an element. We're telling the iterator, right now we're at a specific element, remove it. And that way the iterator can update whatever state it needs to make things work. If instead we replace this with now we're back in the same place. So the lesson is, if you're iterating over, if you want to modify a list you're iterating over, you have to do it via calls to the iterator object. And you don't have to access the iterator object in a for each loop. So that's a reason you may need sometimes to use an explicit iterator object. Yeah?
How did the for each loop know which methods you had to get next? Do you have to have them? Because you were using a custom class before you.
Yeah.
So how did it automatically know which of your methods would be next?
Okay. So the question is, up here, how does it know, how does this for each loop know to call next and has next? Okay. You can only use a for each loop on objects that implement an interface called iterable.
But I didn't see that in your MyList.
We're not using MyList.
Oh, I see.
Right?
Oh, it's the job.
So if we look at linked list, go to the top here, we're going to see that it implements list, and list implements collection, and collection implements iterable, and iterable, among other things, well, it's a long story, but basically, because it implements that interface, then it can assume there's a next method and it has a next method for it to use.
I was confused because I thought it was going over to MyList.
Yeah. Yeah, we wouldn't be able to use a for each loop on MyList unless we'd have to implement the iterable interface. Then we can make it work. Okay. Okay, so just one class left. So remember, the review slides are online in the schedule. Look at them for next time. Come